Hello. In this video, I'm going to show you how to solve this problem involving a resistor, a capacitor, and an inductor. What we'll do, basically what we're trying to do is we are trying to find the charge on the capacitor as a function of time after we switch. So we start out with the inductor is connected to this side, and then the switch flips, connects it to this side, and we want to know what the charge on the capacitor is as a function of time. Okay, so to begin with, let's consider what happens before the switch is switched. Okay, it's presumably it's been that way for a while, so the current has built up. Basically, L doesn't like a changing current. But as long as the current builds up slowly, it doesn't matter. What determines the ultimate amount of current going through is the resistor. So by V equals IR, the current is I is equal to V over R. So before the switch is flipped, that's the current. Okay. We'll call this I initial because after the switch is flipped, this is going to be the current, but that current will change over time. Okay, how will it change over time? So once we flipped it to this side, then the current is going to start flowing around this circuit, and we want to know the charge on the capacitor as a function of time. This is an LC circuit, as discussed in class. LC circuits are kind of like a mass and a spring. They oscillate back and forth. They give you a sine or a cosine. So if we were to plot them, let's do it this way. If we were to plot them, the current as a function of time, it would oscillate like so. Now the question is, when does it start? At t equals 0, is it a high current? We're plotting current as a function of time. Is it a high current at the beginning, or is it a low current, or zero current at the beginning, or a negative current at the beginning? Well, it starts out with the maximum current. So we can plot the axis here. This is I. If it started out with no current, and maybe all the charge started on the capacitor, it would start at the node, or maybe this node. But as it happens, it's starting with all of the current V over R. So this value here is V over R. It then decreases and then oscillates. So this happens to be a cosine rather than a sine. So our current is equal to V over R cosine of, omega t. But as we discussed in class, the oscillation frequency for an LC circuit is like this, LC. Okay, so in class, we had a sine rather than a cosine because, well, either one really works. It really just depends on where you start. In this particular case, we are starting with current being high, so we're starting with the cosine. And then the oscillation frequency, omega, is equal to 1 over the square root of LC. Okay, so that's the current as a function of time. We get the frequency from the fact that it's an LC circuit. We know it's oscillating, so either sine or cosine. We know it's a cosine in particular because it has to start with high current. We know the initial current, this I naught, because we could work out from V equals IR from before the switch flipped. So if you actually look at the current before this, it actually goes back like that. We get flat one. So that if you wanted the current through the inductor as a function of time, it would do that. Okay, let's find the charge. We're asked to find a charge on the capacitor. You may remember that I is equal to dq dt. Basically, the current is charging of the capacitor, or the rate of change of the capacitance is the current. We're trying to find Q, so we're going to basically integrate this, move the dt to the other side, dt is equal to dq. Integrate both sides. And we basically get q is equal to the integral of I dt. We know what I is. I is this thing up here, so we can plug that into our integral of v over r cosine of t over the square root of LC. And we're going to integrate from time equals 0 to time t, dt. The integral of cosine happens to be sine. If you do this integral, you would get q is equal to v over r, the square root of LC sine of t over the square root of LC. Don't believe me? Take the derivative of this. So we take the derivative of sine, we get cosine. Chain rule, take the derivative of the inside, we get 1 over square root of LC. That cancels this LC, and we get the argument here. So because the derivative of this is that, well, then the integral of this is that. Okay, so that's q as a function of time. I should note that it's a sine, so it starts out at 0. Sine of 0 is 0. That makes sense because the capacitor starts with no charge on it, right? It's discharged with just all. We started with a current over here. When we flipped the switch, it charged it up. Okay, so it has to be charged first before it can do anything. Okay, so that's the charge. The charge on that capacitor is a function of time. I should note that whether you have a plus or a minus out front here, you could call this a minus sign. Sort of just depends on which side you call the plus side of the capacitor, which side you call the minus side of the capacitor. I never really specified. So to say the charge would be minus, this would equally be true, since I didn't really specify which side's plus and which side's minus. Okay. Have a good day.